In problem 19, we're introduced to a very important concept. The concept is the nth roots of unity. So the unity in complex numbers is the number 1. So this means the nth roots of 1. Okay. So let's find a formula that tells us what they are, and then we're going to explore them a little bit in parts B and C. So 1 has argument 0, of course, and the modulus of 1 is, of course, 1. So the nth roots, wk, are given by, well, I'm not going to put the modulus to the 1 over nth power because 1 to the 1 over n is 1 as a real number. And so it's just cosine of our argument, which is 0. So I'm not going to write, well, I guess I'll write it. 0 plus 2 pi k over n, and then plus I sine 0 plus 2 pi k over n. And if we were to get rid of that 0, we'd get this very nice looking formula. Cosine 2 pi k over n plus I sine 2 pi k over n. And this is for k equals 0 up to n minus 1. Of course, when k is equal to n, I haven't said this yet, but when k is equal to n, you've sort of exhausted all your possible new roots, and you've circled back. But I encourage you to plug in k equals n and see what you get. So we're going to work this out for a couple of values of n. We're going to start off with n is equal to 3. So when n is equal to 3, we have w naught is cosine of 0 plus I sine of 0. And that's 1. Okay, 1 is a cube root of 1. Check. Great. We're golden. Where's my gold color? Here it is. W1, or omega 1, is cosine of 2 pi thirds plus I sine of 2 pi thirds. And cosine of 2 pi thirds, I believe, is negative 1/2. And sine 2 pi thirds is root 3 over 2. So we get W1 is negative 1/2 plus root 3 over 2i. W2 is going to be, with k is equal to 2 and n is 3, so we're going to get 4 pi thirds for our angle this time. And the cosine and sine of those angles are negative 1/2 and negative root 3/2. Now, I want to observe something here real quick. I want to observe, so this is fine, this is all of them. Actually, let's draw a picture real quick, and then we'll do an observation, which will be helpful for some of your homework. So let's draw our circle. Here's our unit circle, where our w's lie. W naught is here. You always have that as a root of 1. And then W1 and W2 are over here. And we know that since they're cube roots of unity, being cube roots of unity, we know that they solve an equation. So they know that when we plug in, when we cube each one of them, we get 1. This is equivalent to solving. They're not all the solutions to. Well, I guess if we put in 1, then we get all the solutions. Or all the solutions to z cubed is 1. Okay. Now, I want to observe something here. We're going to observe that W1 squared is not equal to W1. Fine. Why is W1 squared not equal to W1? Well, the arguments don't even match up, right? The argument for W1 squared is double the argument of W1. So this has an angle of 2 pi thirds. The argument, oops, let's not do principal argument, but one of the arguments of W1 squared, you have to double that, is 4 pi thirds. So actually W1 squared has the same argument as W2, and has the same length as W2. So what this is telling us W1 squared is W2. Great. And W1 cubed is back to 1. So somehow, to write down all of the cube roots of unity, we really just need one of them. We really just need W1, and then the others come from W1. And that's not always the case, but when that is the case, we will refer to this as a primitive cube root of unity. Because all of the other ones, well, there's only one other one in this case, but in the general case, there's more. They sort of come from W1. All right, let's do n equals 4 now. So our W naught is still going to be 1. Check that. W1 will be cosine 2 pi over 4 plus I sine 2 pi over 4 with our formula from above. And that's I, because that's 0 and that's a 1. W2 is going to be cosine of 2 pi times 2 is 4 pi over 4 plus I sine 4 pi over 4. Now that's a pi. Cosine of pi is -1. Sine of pi is 0. So we get -1 in this case. And then W3 is cosine 6 pi over 4 plus I sine 6 pi over 4. 6 pi over 4 is 3 pi halves, and that's 0. That's -1, and we get -I. So let's draw a picture of these. So here's our unit circle. Here's W0, which is 1. That's our primitive fourth, or our principal fourth root, rather. So W naught, this is the principal fourth root. W1 is I, it's up there. W2 is -1, it's over there. W3 is -I, it's down there. Let's also notice that W1 squared is W2, because I squared is -1. And W1 cubed is, well, it's I cubed, which is -I, because we get an I squared in there for a -1, but then we have our leftover I. And that's W3. W1 to the fourth is 1. I to the fourth is clearly 1. And so, as we saw with the case n equals 3, in the case n equals 4, you kind of just need W1, and the other guys are you can sort of get them by taking powers of W1. You can't do that with W2 though. Hang on, let me say this is a primitive fourth root of unity. W2 is not a primitive fourth root of unity. So let me put here caution. W2 is not primitive because when you just have -1, that's what W2 is, you go back to 1. So you skip over W3 entirely and you will never get W1 from that. So W2 is not primitive. You can't get everything with W2. But it's not hard to convince yourself that W3 is primitive. And if you were to sit here and compute it, W3 squared is W2, and W3 cubed is W1, and W3 to the fourth, W3 to the 1 is clearly W3. W3 to the fourth is 1, and you get all of them just with W3. So there's two primitive fourth roots of unity. There's W1 and W3 as in the picture. All right, so in 19, they also have us asking us to do n equals 5. I think this gets the point across, though, although I encourage you to work out what happens when n equals 5.